Hey Calc, I'm going to start you into 2-3 today. We'll get a little bit of ways through 2-3 homework assignments up here at the top. This is finally getting to the nice part of doing derivatives and like kind of the cheating method, I guess I should say. And so you should like this pretty good. First it starts off so it has like these little, look for these little squares here. Derivatives of a constant, derivative of a power function. It's got different rules as you go through. So they start you off with taking the derivative of a constant number. So like the derivative, let's talk about derivative for just a second. Differentiation is the process of finding a derivative. Process of finding the derivative. Okay, and a derivative is equal to the slope of a tangent line. We also said it's equal to instantaneous rate of change or the velocity at a specific point in time. Okay, so all of those things mean the same thing. In this context, just because we don't have any story problems today, we're going to refer to it more as the slope of a tangent line. Okay, so I'll show you that with this diagram here. But that's what a derivative is. Okay, here is my constant function, this blue line right here. This is y equals c. So let's say y equals 4. Let's say it's up here, 1, 2, 3, 4. And it's y equals 4. Okay, if I am picking a point, which is this guy right here, and I'm trying to find the slope of a tangent line. Now keep in mind, like a tangent line only touches like at one point, right? So like if I have a curve right here and I'm doing the tangent line, it's like this one that just like brushes it and grazes off. But for a horizontal line, like y equals 4, your tangent line is going to be on the line, right? Like it's the only way that that's going to happen is for you to have your tangent line on the line. So what we're doing is we're looking for the slope of this line, and the slope of that line is going to be 0. Okay, so the rule over here says that whenever you're taking the derivative of a constant number, it's 0. So like example 1, the derivative of 1, this is like y equals 1. So a horizontal line up at 1, his derivative is going to be 0. A horizontal line at -3, his slope is going to be 0. A horizontal line at pi, his slope is going to be 0. A horizontal line at -square root of 2, his slope is going to be 0, because all of those horizontal lines are going to have a horizontal tangent line, and their slopes are going to be 0. Okay, so anytime you have a constant function, it just reduces to 0 when you're taking the derivative. Okay, now when you have a power function like x, like y equals x, they've graphed here. Okay, and it's kind of the same type of thing. He's angled y equals x. If I am trying to find the slope of the tangent line at this dot, well, my tangent line is going to live on that line as well, because I can't just like graze it and, you know, just like hit that spot and go on. His tangent line is going to be on that line exactly. So his slope is going to be the slope of whatever the slope of the line is. And in this case, it's 1, because the slope here for x is 1, okay? So the rule for this one is that whenever you have the derivative of x, that value is going to be 1, okay? The derivative of x is 1. Now, let's say I have, we didn't talk about this notation. This guy right here, d over dx, this means the derivative with respect to x. So the derivative with respect to x, d over dx, the derivative with respect to x, okay? We will eventually, when we get to like the end of this chapter, start taking the derivative with respect to like t. When we're dealing with velocity, we're doing things in units of time. So we would have like d over dt instead of d over dx, but that's what that notation means. That just means take the derivative with respect to x. X is our designated variable, okay? We'll also be taking the derivative with respect to y at some point too. So we'll get to that, but that's what that notation means. So d over dx, let's say I'm doing 3x instead, okay? So now I'm looking at this function, and 3x is going to start at 0, and it's going to go up 3 and over 1, so he looks like this, okay? And let's say I'm trying to find the slope of that tangent line, right? The tangent line is going to live on top of there, and so his slope is going to be 3 as well, right? So whenever you have a power function like x or 3x, it's just the coefficient out in front. Okay, now you can expand that to what's called the power rule, which says this, and I've taught you guys the power rule already. It's like if you have, let's go to x squared right here. They say d over dx of x squared. If you take that guy and you're finding the derivative, you take the exponent, you move it down in front, okay, so that 2 becomes here, then you write x, and then you subtract 1 from the exponent. So 2 minus 1 is to the first power. So that's 2x to the first power. That's the derivative of x squared, okay? This guy, x to the third power, the 3 comes down in front, so he's 3x, and then I subtract 1 from the exponent, so he's 3x squared. Okay, that's how that works. Now, we can apply the same principle here. Like, let's say I'm taking the derivative of just x, right? This is like x to the first power. So the 1 comes down in front, right? This is 1x to the, and I subtract 1 from the exponent, which is the 0 power. X to the 0 power goes away, so that answer is just 1. Same thing with 3x. This is 3x to the first power. The 1 comes down in front. Now, since there's already a 3 there, I would just multiply those together. So 3 times 1 is going to give you 3. X to the, I subtract 1 from the exponent, which is 0. And then he goes away, so that is just 3. For a derivative, okay? So the power rule that we do down here also applies to this guy up here. Just remember that if it's just x, it's going to eventually be x to the 0 power, which just will go away, okay? So the rule for the power rule is this right here. Maybe this is what you need to remember, okay? If you're taking the derivative of x to the nth power, okay, the n comes down in front, which makes it n in front, x to the, and then I subtract 1 from whatever that exponent is. The n comes down in front, x to the n minus 1 power. That's how that works, okay? All right, so let's do maybe a couple examples of this. All right, maybe you stop and try to do some of these on your own, okay? For example 2, so it wouldn't be a bad idea to pause the video right now. Try to do maybe these next 3 on your own and see what you get, okay? All right, here we go. The 4 comes down in front. So he's 4x to the, and if I subtract 1 from the exponent, he's 4x to the third, okay? The second one, the 5, is that a 5? 5 comes down in front, or a 6, whatever that is, 5x to the, if I subtract 1, that's to the fourth power, okay? Next one, the 12, he comes down in front, so 12t to the 11th power. Okay, this one was d over dt because that's what my variable is designated, okay? So, yeah, that's what we'll end up doing later on in the chapter. We'll just have it in terms of t instead of in terms of x, and that's totally fine, okay? So, not terribly hard once you know the pattern. It's, like, pretty easy, right? So now, let's go to, this one, example 3. They want us to find the derivative of x to the pi. Okay, well, here we go. We want pi down in front. That number, this number, because pi is a number, comes down in front, x to the, and I'm just going to leave it as pi minus 1 power, because if we write it as like 2.14, that's not what pi is. Pi continues on forever, so I want to just leave it in terms of pi, so I'm just going to write it like that. Pi to the, or pi times x to the pi minus 1. Okay, now, this guy right here. This is where it gets a little tricky. Because you have x in the denominator. So what I'm going to do is, before I start to take the derivative, I'm going to move the x to the top. And this is going to be 1x to the negative first power, right? Because he's to x to the first power on the bottom. If I move him to the top, he's to the negative first power, okay? So this is how I'm going to think of him, is 1x to the negative first power. If you don't like that 1 being here, we can erase this 1 in front, right? Whoop. And just have x to the negative first power. Okay, it doesn't matter. So now we apply the same principle. This guy comes down in front, so I have negative 1 down in front, x to the, and I want to subtract 1 from the exponent, okay? Negative 1 minus 1 becomes negative 2, right? A lot of people think that comes out to be 0. It doesn't, right? You're thinking whole numbers. Now you're in a negative number. Negative number minus another negative brings it down even further. So that's negative 2. Now if we fix him, I want to move this x to the 2 back down to the bottom to make it positive. So this negative 1 is going to stay on the top, and he's going to become x to the positive 2 power on the bottom, okay? And that's what the derivative will look like, okay? So he is all done. All right, this one is in terms of w, so d over dw. That just means the derivative with respect to w, Okay, all right, so this guy, if I move him to the top, he is going to be w to the negative 100 power, right? He'll become negative when you move him to the top. It's like over 1 now, like the w used to be down here, and now the w is on the top, okay? So w to the negative 100 power. I'm going to move that 100 down in front, so negative 100 w, and I'm going to subtract 1 from the exponent. Okay, what's 100? Negative 100 minus 1 is negative 101, okay? Now if I move him back down to the bottom, the 100 gets to stay. He gets to stay in the top. And this is negative 100 over w to the 101. Okay, that's what he will look like. All right. Okay, x to the 4/5 power. Now, they could have done this really hard, and this is what they're going to do in the next problem. X to the 4/5 power means the 5th root of x to the 4th. That's what that means, okay? But when we take the derivative, we want it in terms of this. So this guy, we're going to have to switch him, okay, before we do the next piece. Okay, we want him as written as x to the 4/5 power before we take the derivative, okay? We just, same rules apply. We want to take the 4/5, we move it down in front. So this is 4/5 x, and then I subtract 1 from the exponent. Okay, now 4/5 minus 1. If you find a common denominator, minus 1 is like minus 5 over 5, right? 1 is like 5 over 5 if I find a common denominator. So 4/5 minus 5/5 is negative 1/5. Okay, 4/5 minus 5/5, negative 1/5. Okay, now technically this x is in the numerator, so if you put him up here with the 4, that's technically true. But if I want him to be a positive 1/5 power, I'm going to move him back down to the bottom with the 5. Okay, kind of confusing. 4 over 5, and then I have x to the 1/5 power. Now he's underneath, right? Like x right now is like slid off to the side, right? Which means he's in the numerator. So if I put him underneath, he's now on the bottom with the 5 to the 1/5 power. And then if you want to, you can make the 5th root of x. Okay, so 4/5 and then the 5th root of x on the bottom. That's a 5, by the way. So there you go. That's the derivative of x to the 4/5 power. Okay? All right, here we go. The cubic root of x. Okay, we don't like to have him as a root like this one. I don't want him in terms of that. I want him as a fractional exponent. So we're going to instead write him as x to the 1/3 power. That's what the cubic root does. Okay, then we're going to take this 1/3. We're going to move him down in front. We're going to make him 1/3 x to the, if you subtract 1, okay, subtracting 1 and finding a common denominator of 3, this is like subtracting 3 over 3. Okay, and 1 over 3 minus 3 over 3 is negative 2 over 3, right? 1 over 3 minus 3 over 3 is negative 2/3, okay? Now, technically, this x is in the numerator, even though he slid off to the side, so if I want to move him back down underneath, it'll be 1 over 3 x to the positive 2/3, okay? And then if you want, you can switch him and make him 1 over 3 and the cubic root of x squared. And that's what his derivative will look like. That's so exciting. You guys are doing derivatives. Very nice. Okay. Good, good. Okay. All right. I'm going to only do just a little bit more. I'm not going to snow you too much today. Or maybe I've already snowed you. I don't know. Let's do the derivative of a constant times a function. And I've already done this one up above when I talked about the 3. So like the 3, if there's a 3 here, and you move the 1 down in front, you just take 3 times 1. If there's already a constant there, you just multiply the exponent by that number, okay? So here, like example 4, we take this 8 and we want to move it down in front. But if there's already a 4 there, all I'm going to do is take that times 8, right? 8 times 4 is 32. X to the, if I subtract 1 from the exponent, he's now to the 7th power. Okay, so if there's a number down in front of there, no big deal. Just multiply him by the exponent. Okay, same thing here. This guy is technically a negative 1. Okay, so I want to take this 12 and I move him down in front. Negative 1 times 12 is negative 12. And x to that, if I subtract 1 from the exponent, that is 11. Okay, we'll do one more and then I'll talk to you about some stuff here before we go any further. This guy, I don't want the x in the bottom, so I'm going to bring him to the top so that I can take the derivative. So he will be pi x to the negative 1st power all over 1. right? Or you don't have to have that 1 on the bottom there. We've moved him to the top. He was x to the first power. Now he's x to the negative first power. Okay, so now I'm looking at this being the x. Pi, this is going to be a little confusing because pi is a number. Pi is just like 4 or -1. Pi is a number, all right? You're going to take the -1. You're going to move it down in front. -1 times pi is going to be negative pi. X to the, if I subtract 1, -1 minus 1 is -2. And now I want to fix that -2 power, so I'm going to move him down to the bottom. So that is negative pi over x to the +2 power. Okay, and that's what his derivative is. All right? Okay, so don't stop listening. I'm going to wait till tomorrow to go on to the rest of it, but here is what this does. Okay, way back when, like last week, when we were doing derivatives, we would do this function. The limit as h goes to 0 of f of x plus h minus f of x over x minus h. No, just over h, okay? All right, so here's the deal. We would do this, and let's say just to this first guy, 4x to the 8th power. Let's say that's my function, 4x to the 8th power. We're trying to find the derivative, and I want to do this process to him, okay? So here's how this would work. I would do the limit as h goes to 0, and then here f of x plus h. I would take x plus h and I would plug it in for x. So I would have 4 times x plus h to the 8th power, right? Instead of x, it'll now be x plus h. Minus f of x, which is just the original, 4x to the 8th power, all over h, okay? And when we did this, we're not going to continue on from here, because when we did this, we would have to take x plus h to the 8th power and FOIL that 8 times. And then minus the 4x to the 8th, which might cancel a bunch of things, whatever, divide by h, and then we'd plug in, right? The plug in 0 for h, because h would cancel somehow, and then we wouldn't have any h on the bottom, and then we'd plug it in, and we would get an answer. And that answer is going to be 32x to the 7th power. That's what he will end up being. Okay, after all of that, after you FOIL it 8 times, blah, 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 all that stuff, doing that process, that's what he is. And we can just do it with the power rule now. Okay, so it's not so bad if you only have like squared or something, but like 8 powers, I don't want to do that. I want to do the power rule, okay, where I can just do it in my head and get an answer just straight from here. Like that's all. I didn't even have to show any work, really. I could just do that in my head versus this limit process, which is what we were doing before, okay? So that's what we're getting to. And again, this guy is a derivative. This is a slope of my tangent line, okay? So if I map out what 4x to the 8th power is, okay, he is going to be like, I don't know, probably have like a bunch of bubbles here, whatever, right? Like that, okay? Now, how is this thing supposed to be a slope? Well, it kind of is, except I haven't told you where I want the slope at. Maybe I want the slope all the way over here at 12. Maybe that's an x-coordinate of 12. I want the slope here at 12, right? I want the slope of that tangent line at 12. So I take 12 and I plug them in here, and that's going to give me the slope of that line, right? Or maybe I want the slope here at 0, right? And I do that, okay? If I plug 0 in, 0 to the 7th power times 32, he's going to have a slope of 0, right? Okay, so he is a slope, but I need to specify where I want that x to be located before you plug a number in. Okay, so don't think slope is like it has to be one number. It will be a number as soon as you plug an x value in there, okay? All right, so I won't go any further than that. We will stop there, but you should be able to do some of the homework problems. 2 through 10 evens, 18, 40, and 64 is what we've done for homework. So try to get through at least the first little bit, and we will finish more notes tomorrow. Goodbye.